So if we wanted to think of this as kind of a coordinate, you could call this 1, 0, 2, 2. And one of the first things we're starting to realize is, wait. What does this look like visually? Because once we extend it to 3D, it's like, oh, okay, well, now we just have a z-axis, so it can be an x, a y, and a z. Now if I have some output here, did I make a mistake? Minus 4.
Zero.
So this is a 4-dimensional thing. So really what it's saying is when you open up along the x-axis, the y-axis, the z-axis, the w-axis, you're going to go up to 2. You can still think about that in 3D. Maybe this is saying in 3D space, now your input is something in R3. When you go to the point 1, 0, 2, maybe you can think of this as something like the temperature at that point, or the air quality. It's not going to be some sort of length anymore, but you can assign some sort of meaning to a function of 3 inches. It's still possible to think about. Questions about it? The next thing, you can still compute partial derivatives. And the beautiful thing is it works all the same as we were doing before. This is saying compute the partial derivative of f with respect to x. So x is the variable, you're going to take the derivative with x, everything else is a constant. But now you can take the partial derivative with respect to z. Because now that is an input of this function. So it behaves the same way. Compute, when we wrote this upside down triangle, we called this the gradient vector. So just thinking back, the last ones we were looking at, the gradient was just a 2D vector, partial derivative with respect to x, partial derivative with respect to y. Now, you're just going to have a 3D